Hey, welcome to the video. This is part of my series where I break down the core ideas behind distributed systems and databases, the kind of stuff that's running under the hood of systems like DynamoDB, Cassandra, and Kafka. Today we are looking at Merkle trees, a data structure that lets you figure out which pieces of data are out of sync across two machines without comparing every single record. It's elegant, it's efficient, and once you see how it works, you'll start noticing it everywhere. Let's get right into it. Imagine you're building a distributed database. You have 3 nodes and every key is replicated across all 3. A user writes to node 1, another user writes to node 3, and because you are prioritizing availability, you accept both writes, even though the nodes haven't talked to each other yet. Now you have a problem. The replicas have diverged. Some keys on node 1 don't match node 3. You need to find out which keys are out of sync so you can fix them. The naive approach? Compare every single key across both nodes. If you have a million keys, that's a million comparisons every time. That's big O of n and it's brutal at scale. DynamoDB solved this problem with a data structure called a Merkle tree. And the elegance of it is that instead of comparing a million keys, you can pinpoint exactly which keys have diverged by comparing maybe 20 hashes. Let me show you how. Let me give you a bit of context first. In a system like DynamoDB, every key is replicated across n nodes. When a write comes in, one node acts as the coordinator. It forwards the write to the other replicas. The write is considered successful when W nodes confirm it. Reads work the same way. A read succeeds when R nodes respond. And if you set R plus W greater than n, you get strong consistency because the read and write sets always overlap. You are guaranteed to read the latest write. But DynamoDB chose a different path. They prioritized availability. They wanted to never reject a write, even during node failures and network partitions. The trade-off is that replicas can temporarily drift apart. A write might succeed on 2 nodes, but miss the third. That's eventual consistency. The replicas will eventually converge, but in the meantime, they might disagree. So the question becomes, how do you efficiently figure out which keys have drifted? Before we get to Merkle trees, we need to understand how DynamoDB tracks changes. It uses something called vector clocks. A vector clock is just a list of node counter pairs attached to every key. Each time a node modifies a key, it increments its own counter. So if node A writes to user colon 1 to 3 twice and node B writes to it just once, the vector clock might look like node A equals 2 and node B equals 1. When you compare 2 versions of the same key, you compare their vector clocks. If one clock is strictly greater than the other in every entry, that version is a descendant. It's newer and you can safely keep it. But if neither clock dominates, say one has node A equals 2, node B equals 1, and the other has node A equals 1, node B equals 2, then these versions are concurrent. They have diverged and the system needs to resolve that conflict. But here's the thing. Vector clocks tell you whether a specific key is inconsistent. They don't tell you which keys to check in the first place. If you have a million keys replicated across 2 nodes, you would have to compare the vector clock of every single key to find the ones that have diverged. That's the O of n problem. This is where Merkle trees come in. A Merkle tree is a binary tree where every leaf node is the hash of a data block. In our case, each leaf is the hash of a key value pair and its vector clock. Each parent node is the hash of its 2 children concatenated together, and this bubbles all the way up to a single root hash. Here's why this is powerful. If even one key changes on a node, its leaf hash changes. That change propagates upward. The parent hash changes, the grandparent hash changes, all the way up to the root. So to check if 2 replicas are consistent, you just compare the root hashes. One comparison. If they match, every single key is identical, you're done. If they don't match, you recurse. Compare the left children, compare the right children. Whichever side differs, you go deeper. You keep narrowing down until you reach the leaf nodes that actually changed. The beauty of this is that you skip entire subtrees that match. If the right half of the tree is identical across both nodes, you never even look at those keys. You only traverse the branches that contain differences. Let me walk through a concrete example. Say node 1 and node 2 both store 4 keys. Node 1 has key 0 equals value 0, key 1 equals value 1, key 2 equals value 2, and key 3 equals value 3. Node 2 is identical, except key 1 has a different value. Everything else is the same. Both nodes build their Merkle trees. Node 1's root hash is, let's call it ABC. Node 2's root hash is XYZ. They are different, so we know something has changed, but we don't know what yet. Let's start off with step 1. We compare the root hashes. ABC does not equal to XYZ. So the trees differ, and we recurse into the children. Step 2. We compare the left children first. Hash AB does not equal hash XY. So the left subtrees differ. When we compare the right children, hash CD equals hash CD. The right subtrees are identical, and thus we skip the entire right half. We just eliminated key 2 and key 3 from consideration without ever looking at them. Now moving on to step 3, we compare the left-left leaves. Hash of key 0 matches, so we skip. When we compare the left-right leaves, hash of key 1 does not match, and we found the difference. Key 1 is inconsistent. We checked 3 nodes to find one difference out of 4 keys. But with a million keys, this scales logarithmically. You might just check 20 or 30 nodes instead of a million. Merkle trees are part of a bigger family of techniques called anti-entropy mechanisms. These are the tools distributed systems use to detect and repair the inconsistencies that naturally happen in eventually consistent systems. Read repair fixes things on the fly. When a read detects a stale replica, it immediately updates it. Hinted handoff stores writes temporarily when a target node is down and delivers them when it comes back. Gossip protocols let node exchange state information to discover inconsistencies. Merkle trees fit into this as the background synchronization layer. Periodically, nodes compare their Merkle trees to find diverged keys without transferring actual data. It's a lightweight consistency check because you're just comparing the hashes and not shipping entire key value pairs across the network. One important trade-off to think about is the tree depth versus rebuild cost. A shallow tree with more keys per leaf is cheaper to rebuild when data changes. But when you're comparing trees, you might have to check more keys in a mismatched leaf bucket. A deep tree, on the other hand, with fewer keys per leaf pinpoints differences precisely, but rebuilding it after every write is more expensive. Most production systems land somewhere in the middle, 16 to 64 keys per leaf with incremental updates instead of full rebuilds. And Merkle trees aren't just a DynamoDB thing. Git uses them for content verification. Bitcoin uses them for transaction validation. Any system that needs to efficiently compare two large datasets uses some variant of this idea. The core insight is simple. Hash your data into a tree, and you can find differences in logarithmic time instead of linear. It's one of those ideas that once you see it, you wonder how do you do it any other way. That's it for this video. If you enjoyed this, check out the blog post link below for more detail. Thanks for watching.